Welcome everybody, this is the last part in the OpenHBI Parallel Programming Concepts course. So I'm very happy that you stayed with us until this very last video. In this final presentation we now want to give a short summary of what you heard about, what may be the highlights from your point of view or at least from our point of view, so that you have a good wrap-up of all the different things we talked about. So the last 6 weeks we spent some time in discussing a lot of topics that can be related to parallel programming. The name of the course is Parallel Programming Concepts, so the idea was always to give you a broad overview of what is going on in the field. And you see here again the week structuring. Most of the terms should be now familiar to you, not in the sense that you're an expert in one or the other topic, but that you at least have a rough understanding of where you can put this. So the point of this course was always to mention terminology, concepts, programming paradigms, hardware concepts, things that are relevant now when you want to tackle parallel programming. And our hope is that you can now take this knowledge and start to concentrate on one or the other aspect more deeply in order to solve your maybe existing parallelization problem in practice. So let's go through the different weeks again shortly. What you will see now is basically a copy of earlier slides. Nothing in here is new, so please take this just as a summary. We started in week 1 with the overall understanding of the fact that the free lunch is over, Herb Sutter and his famous quote. So we have the situation in hardware that for roughly 10 years now the clock speed is flattened, that the performance increase in processor hardware no longer comes for free, but instead we have the problem that processors, although Moore's law is still valid, are equipped with new cores instead of higher frequencies and more fancy ILP technology or more powerful ILP technology. So we had this generalized statement based on the Feistor quote, where we said, how can you do anything faster, because parallelization is about getting faster, getting better, solving a bigger problem. And we had these 3 ideas: work harder, work smarter, and get help. And it turned out in week 1 that power wall, memory wall, and ILP wall basically are all problems that are existent. And despite the memory wall, we hopefully can deal with them through parallelization. So we get the speed, the additional speed for our application, no longer by increasing the frequency or by having smarter ILP or larger caches, but we now get the increased speed by utilizing additional cores or additional processing elements. And this is the parallelization trend. This is the reason why parallel computing and parallel programming is now so relevant in comparison, for example, to what we had 20 years ago in computer science education and in software development education. So in practice, we see that we have parallelism on different levels. We may have a processing element where you can run multiple tasks, at least concurrently, but maybe also in a parallelized fashion. So we talked about instruction level parallelism, for example. Then we have shared memory systems with processing elements that share a common main memory. We saw that this is a very simplified thinking, because you have things such as UMA and NUMA architectures. So memory may have different hierarchies for these different processing elements in the same system. And then we have the world of shared nothing systems, where we have processing elements, multiple of them typically in a box with their own local shared memory. And all these boxes then communicate over a network link by some messaging facility. And the parallel programming problem now is that we have these execution environments given in hardware, and they constantly evolve. So they have a particular type and a particular configuration in our environment. And we have our parallel application. And the question is now, how do we design the parallel application? That's the first part. How do we take these parallel application and match it to a particular execution environment? That's the second part. So these 2 things must be solved. The third part may be then how to organize our execution environment in a way that it fits to a maybe already existing parallel application. And week 1 also showed us that there are 2 fundamental laws in parallel computing, and we think it is very relevant to know both of them, because both of them are valid and both of them have their place. Amdahl's law talks about the idea of getting speed up by adding more processing elements, more cores, more processors, for the same kind of problem. So you have one piece of problem, it doesn't change, you parallelize it, and the question is now, how much do you get from adding more resources? And it turns out that with Amdahl's law, there is always a capping. So you can't endlessly put new cores, new processors, new machines into your cluster and expect that the application runs faster. This is not possible because you have the inherently serial fraction, and this eats up your performance so that at the end it all relies on the part of your application where the serial stuff takes place. And this is bad, but we have also Gustafson's law, and Gustafson's law says us if you don't get speed up for a problem of the same size by adding more resources, you get at least a benefit from adding more resources when you take a bigger problem. So adding more resources does not speed up the same problem size, but it allows you to process a larger problem in the same time. And surprisingly, it turns out that today, when you look into, for example, big data problems, that Gustafson's law is way more important. So people are not really aiming for making one particular parallelized computation faster. What they're really aiming for is processing more data, processing more elements, doing more computation in a fixed time. And so Gustafson's law is the one where we would say that this is really crucial today, and that it's somehow the argumentation that all these parallelization attempts and all these hardware developments really make sense. In week 2, we then went towards to concurrency and parallelism, and this was more like a theory week, so we didn't talk too much about precise mechanisms in practice, but we really tried to nail down that there is concurrency and then there is parallelism. Concurrency is an abstract property of your software, so you try to write concurrent software, and then you can run these concurrent activities in your software, hopefully in parallel, if you have parallel hardware available. And this leads to the surprising fact, or to our interpretation, that parallel programming is actually concurrent programming, because you deal with concurrency aspects, and if you do it in the right way, then it also runs in parallel. After these 6 weeks, you also know now that parallel programming is a little bit more than concurrent programming, because you also have to consider the speed-up question. So when you do your parallel software, yes, it is concurrent with respect to the problems you may get, for example, race condition-based problems. But if you have done that, you also want to achieve some speed-up or some scaling from your parallelization. And this is the point where you have real parallel programming, and the fact that you need to use your existing hardware in the right way. So parallel programming is really a combination of concurrent programming and optimizing for performance by several tricks and smart approaches we saw in the last 6 weeks. We used, we tried to use at least a common terminology in this course based on the proposal by Madsen. So we tried to talk about tasks and execution units and processing elements. This is basically the fact so that we have a common language to talk with each other. As I already mentioned earlier, you will figure out that in literature, people use different words for different things. So in your own project, I would recommend that you really make a first step to define a common terminology between all the developers and maybe also your customers, so that you talk about the same thing. And this is our proposal for a good terminology, but there may be also other ones that are completely valid. We talked about concurrency issues in week 2, and we identified that there are things like deadlocks and live logs. And this is something that is nasty, but it doesn't go away. So whatever your parallel programming paradigm is, you will always face these concurrent issues, because parallel programming to a good part is also concurrent programming. So these things are there, and you should try to reduce these problems by using smart programming approaches, such as with Actors, for example. In week 3, we then started to look into shared memory programming models. So there is this classical distinguishing between concurrent processes, concurrent threads, and concurrent tasks. And we looked into different approaches. Also, we saw that if you start to split up your work, there's basically the distinguishing between task parallelism and data parallelism, which relates to the question of how do you partition your problem. And the most famous programming model for task parallelism in shared memory systems today is OpenMP. So this is like the default meanwhile, which is a good thing, because people at least have this common denominator to write parallel software. OpenMP has a couple of basic principles that also can be found in other programming paradigms, such as the fork-join parallelism idea. And this is the, let's say, lowest level of parallelization you can do in a shared memory system. If you want to go higher, or if you want to reuse existing solutions, programming languages typically have a lot of high-level concurrency support. This relates especially to data structures, such as concurrent queues, concurrent hash maps. So our strong recommendation is, in your favorite programming language you use, please try to identify these existing implementations of concurrent data structures, because they save you from a lot of issues and they can really help you in avoiding race conditions in your own code. We also talked about more fancy ideas, such as the partitioned global address space concept. This is ongoing research, so we can't claim that this is something that is proven in industry practice, but at least it looks like a good idea in order to deal with the expectable future hardware developments. So take this just as a hint and a nice outlook into what may become relevant in the future. We will see if this is really happening or not. In week 4, we had Frank Feinbube with his week about accelerator programming with our special focus on GPUs. And there you could see that accelerators are a very interesting strategy to get a lot of speed up for comparatively low costs. So accelerators have a completely different hardware architecture in comparison to classical CPU-based systems. And this gives you the chance to write software that really gets a lot of speed up by leveraging these resources. The price you pay is that you have to deal with all the special programming models and the special understanding. We see a trend that these two things emerge. So CPU-based parallel programming and GPU-based parallel programming start to get closer to each other. And maybe we will see at the end that the programming models are combined or unified. But at the moment, this is still two worlds. So you have to really think about accelerator programming and CPU-based parallelism as different things with different technologies and different APIs. This mainly relates to the fact that these two worlds have really different hardware design. So a CPU uses a large portion of the transistors on the die for caching, while a GPU uses the comparatively large portion for processing elements. So memory latency hiding, for example, works completely different in GPUs than in CPUs, and you need to consider this also in your software development. And we learned in week 4 that the basic, let's say, common programming model meanwhile is OpenCL. We also have things such as NVIDIA's CUDA, but if you want to have something that is abstracting from different GPU types, then OpenCL is hopefully your choice. It has its own hardware model. It tries to consider also the fact that your code may run on a CPU-based system. And things evolve there, so there are ongoing trends and interesting ideas such as OpenACC, which give you even a higher level abstraction from these concepts. So a lot of things are going on there, and we will see where this leads to. But this OpenACC, OpenCL, OpenMP are really parts where you need to pay attention also in the future, and you need to check what is going on in parallel programming world. GPU-based programming is also a big question of optimization, of performance tuning. So you see this big table, we had a lot of different concepts here. And the basic idea is take existing literature, take a good book, take a good tutorial, and try to understand these strategies. And especially try to understand if these performance optimization strategies are really relevant for one particular class of GPU hardware, or if this is a general problem, such as latency hiding. In week number 5, we then moved over to shared nothing systems, and we talked about the basic concepts there and the parallel programming concepts. And in shared nothing systems, everything is about message passing. So the idea is that you write your software in a way that you no longer assume a globally accessible shared memory between all the parallel tasks, but you need to make communication explicit. And this is an interesting point because this really flips your whole algorithm design into a different area. You need to think differently about what is important, what kind of data exchange do I need, can I really reduce the messaging part here, can I have more local communication. This is an area where the high-performance computing people have really decades of experience. So whenever you think you target shared nothing systems with your parallel programming, please start to consult what is available from the HPC people, because they have a lot of things to tell and a lot of experience to deliver to you that may help you in your own parallelization problem. So in shared nothing world, we have clusters and we have supercomputers, and supercomputers are like the final thing or the bleeding edge class of hardware you can find here. And this is interesting because in the past it happened often that HPC people, supercomputing people had parallelization problems 10 years before everybody else had them. So this is a rough number, so it's not specifically proven, but overall the experience is that in supercomputing things happen earlier, especially parallelization problems happen earlier. So it's always a good trick to look into their problems and into their approaches in order to have a good future view into what will happen, for example, on the server market or classical server applications in terms of parallelization problems. One of the main takeaways, hopefully, of this course are basic principles or relationships of different problems. So one example is the surface to volume effect, because this is something that is applicable in each and every parallelization problem. This is not really specific to one or the other hardware or one or the other problem class. You have this problem all the time. And so it's good to keep that in mind, similar to Amdahl's and Gustafson's law, that there are these rules or so-called laws that are valid whenever you do a parallelization attempt, and so please consider them in whatever you do in your parallel coding. We talked about message passing and the idea of SPMD. So in message passing, you typically have a cluster execution model where a submission host is delivering a binary to multiple machines, and then you have an SPMD style of programming where you have one single piece of code, and this is now run in multiple instances of your on your node in the cluster. These instances do communication. They do this communication organized based on their own rank, and this model is proven in shared nothing world and is a very common approach to deal with the scalability of such applications for an increasing number of nodes. A more elaborate concept is the actor model. We also saw that in week 5, where we have still the idea of message passing, as for example in MPI, but we have this idea of asynchronous send and the mailbox. And this gives us some tools in order to avoid race conditions in a better way. It also helps with scalability problems. So the overall concept is very nice and helpful, and it's somehow surprising to see that ideas being created in the 70s now become really relevant and interesting in 2013 when we talk about modern parallelization approaches. And in this week, in week 6, we then finally had a short look into parallelization patterns, into classifications of solutions, and this is basically the point where we can just recommend to maybe buy one or the other book, because this is a very comprehensive summary of ideas and best practices you may need when you want to do parallelization. So this is beside the tutorial or the language guide in your favorite parallel programming language. This is maybe the second class of book you want to have in your shelf, that you can rely on these patterns. You can also use online resources. So most of the things we talked about are available online. So try to use these resources and try to use as much knowledge and ideas from other people as you can, because parallel programming at the end is simply complicated. We also saw the Berkeley dwarfs, which is a categorization of parallelization problems. And if you want to get in contact with us or give us some feedback, we would be really interested in your parallelization problems. Do they relate to the Berkeley dwarfs or not? Do you have completely different things to solve? Is this really still parallelization? So this is something that is still open for discussion, also in the research community. And then finally, we had Foster's methodology, and we talked about this comparatively late for a very good reason, because in our own experience, in our HPI courses, and also in the work with students, it turned out to be a very good tool to structure the process of parallel programming. So whatever kind of parallel programming concept you want to use in practice, Foster's methodology is a nicely understandable and very well-structured way of going through the process, of parallelizing your codes, of finding a good and feasible solution that gives you either scaling or a better speed up of your application, so that you really make use of your parallel execution hardware. And with these words, finally, I have to say that's it. We are at the end of the course. It was really a pleasure for me to be your guide together with Frank Feinbube. Summary, we just have to admit parallel programming is hard, but it's also exciting again. So we have now really a lot of trends, a lot of things going on, active research, fascinating industry developments, fascinating new hardware, fascinating new software. We go from massively parallel hardware, either on the desktop with your GPU or in a big cluster, up to complex software systems, thinking, for example, about big data processing environments, all these things, MapReduce approaches. So a lot of activity is going on. On the other hand, you have a lot of foundational facts existing now, design patterns, specific languages. So you have choices, endless choices, what to take. And hopefully this course enabled you to do a better pick in these choices and say, okay, this is good for me or not. That was our intention, at least in this course, to give you an overview in the way that you can make better decisions in your parallel programming attempt. Please consider the basic underlying issues you will have all the time, like, for example, am I compute dependent or I/O dependent? Do I have deadlock problems or not? Before you start with your performance tuning, but when you start with your performance tuning, you really need to understand your execution environment. So we think that in this big area or in this big room of possibilities and solutions for parallel programming, there are some general concepts. We try to nail them down, so hopefully you can use this course as a starting point. Please learn from the HPC people. They have the most experience in this field, and this hopefully gives you then a chance to go through the jungle of solutions and frameworks and languages in order to get the best possible and the fastest implementation, parallel implementation of your problem in your particular environment. And by this, I would like to thank you for your participation. It was really a pleasure. We had lively discussions in the forums. So we learned a lot too about how you deal with these problems, what we need to do better in the teaching and in the explanations. I have to say sorry again for some kind of flaws we had with the material. This happens in such a course, so we did our best and we also tried to improve. Please use the feedback link we provide on the next page. And if you want to stay in contact with the lecturers, we have some links here. So we would be interested in your feedback in one or the other way. And with this, I want to say goodbye. Thank you.